Hello guys, welcome to my YouTube channel. So in this video, we're going to talk about the fatty acid oxidation. Now if you haven't watched my video on the mobilization of fats, then actually you want to know where we are heading to. So I'd prefer that you go and watch my video on the mobilization of fats, how we broke down the triglycerides into its various components. Those are the fatty acids and the glycerol. And we said in that video that we are going to take those fatty acids into various tissues of the body. For example, we said that we take them to the cardiac muscle. We will take them to the skeletal muscle. We can also take them to the liver. And liver is very important because we can synthesize ketone bodies there, and we are going to see how we are going to make that happen. Now, specifically now in this video, we are going to see how we're going to break down the fatty acids until we form now acetyl-CoA. You know, the main aim of mobilization of fats and also the oxidation of fatty acids is just to synthesize energy, ATP, because the initial cause of this particular problem was that there was low blood glucose level, and we need to find a mechanism to provide energy for the body to run a series of metabolic function and also physiological functions of the body. Now, let us now see what's going to happen. Now, this is just an example of a cell, so maybe from the cardiac or the skeletal or the liver. This is just a general example. So, we said that we are going to bring those the fatty acids. So, we have our fatty acids getting into the cell. And we are going to discuss specifically the palmitic acid. Now, palmitic acid is a 16 carbon. Let me just write here. Palmitic acid is a 16 carbon saturated fatty acid. Now it's going to get into the cell, so I'm just going to draw the palmitic acid, but I'm going to summarize how I'm going to do that. So I'm just going to describe the long carbon tree. So CH2, CH2, C double bond, and O, right? So that is palmitic acid. This is the first carbon, alpha carbon, beta carbon, as you go the other way. Now, we have the palmitic acid inside the cell, but now palmitic acid can easily come out of the cell. So what are you going to do? We want to commit it down to, we want to commit it so that it can undergo the downstream processes. So what's going to happen? We are going to convert this palmitic acid into a new molecule. Right. So what are you going to do? We are going to add a CoA, coenzyme A, to be connected to thiol, right? And this process is going to require some energy. So we're going to take some ATP and convert it into AMP plus a pyrophosphate. We're going to utilize 2 molecules of phosphate. Then what are you going to form? You're going to form a CH2, C SH. We've added in a CoA. Now the question is, which enzyme is going to catalyze this reaction? Now this reaction is going to be catalyzed by a particular enzyme, and this enzyme is going to be called fatty acyl-CoA synthetase. This is a pretty cool enzyme. It's going to add in coenzyme A onto the palmitic acid, and the process is going to require 2 molecules of phosphate or the pyrophosphate. Then you're going to form now this one is called fatty acyl-CoA. I mean, you can just say acyl-CoA. Alright, now we cannot, now the acid has not been committed inside the cell, now it cannot get out now. So the process or the problem now comes in. We need to undergo the beta oxidation, but now beta oxidation occurs inside the mitochondrion. This is the mitochondrion. So what are you going to do? We need to get the fatty acyl-CoA into the mitochondrion, but now it cannot get in as fatty acyl-CoA. So what is going to happen? You're going to add in a particular molecule, enzyme. Now we are going to remove the coenzyme A and replace it with another molecule. So we are going to, so inside the cytosol there is a molecule called carnitine, right? So carnitine is going to come and we're going to get rid of the CoA. Alright. So what are we going to form? We are going to form RCH2 CH2 carnitine. Alright. So this is called fatty acyl carnitine. Now, fatty acyl carnitine has the ability to get into the mitochondrion by the help of a carnitine translocase. Now, this transporter here is called a carnitine translocase. But now, before we get into that, we want to see which enzyme added or removed the CoA and added the carnitine. So, the name of this particular enzyme is pretty cool. Now, this enzyme here is going to be called CAT1. CAT1. So it's called carnitine acyl transferase 1, or don't be surprised to see in other books written carnitine palmitoyl transferase 1. That is the CAP, carnitine palmitoyl transferase 1, CPT1. Now it's going to remove the CoA, then add carnitine, so that we are going to have fatty acyl carnitine. Then fatty acyl carnitine now has the ability to enter the mitochondria. Alright, so we have the fatty acyl carnitine. Right. Now, guys, you have another problem. The fatty acyl carnitine cannot undergo beta oxidation. So what are we going to do? We need to replace the carnitine with a CoA. So what is going to happen? There's another enzyme here. This enzyme here is called carnitine acyl transferase 2, or CAT2. Carnitine acyl transferase type 2. So what it's going to do is going to remove this carnitine here and going to add in a CoA. So we are going to do what? Going to add in a CoA. There's going to get rid of the carnitine. Then carnitine, this is a bidirectional transporter. The carnitine translocase is a bidirectional transporter. So carnitine can easily come out into the cytosol. So you have a carnitine back into the cytosol, so that it can now catalyze another reaction. It can now combine and replace the CoA in another, maybe the oxidation of another fatty acid. Now what are we going to have? We're now going to have our CH2. We have our fatty acyl CoA. Now, this fatty acyl CoA now can undergo the processes of beta oxidation to yield acetyl CoA, which can be taken to the TCA, UTC yield energy in form of ATP. Now, guys, let us do a quick recap so that you can see what happened. We said that we are going to bring now the fatty acids from the mobilization of fats or the mobilization of triglycerides, then bring them into the cell. When it gets into the cell, we want to commit it so that it doesn't come out. So we're going to add in a molecule of CoA. The process requires ATP. Now this process is going to be enhanced by an enzyme called fatty acyl CoA synthetase. Fatty acyl CoA synthetase is going to add in a molecule of CoA into the fatty acid, and in this case the palmitic acid, which is a 16 carbon saturated fatty acid. Then you are going to form fatty acyl CoA. You can also call this fatty acyl CoA. Now it has a CoA. Now what is going to happen? Fatty acyl CoA cannot enter the mitochondrion, and it is inside the mitochondrion that you do the beta oxidation to break down the fatty acid. So inside the cytosol there is a molecule called carnitine. Now carnitine is going to replace the coenzyme A, and this is going to be done by an enzyme located on the outer side of the mitochondrion called carnitine acyl transferase 1, or carnitine palmitoyl transferase type 1. It's going to remove the CoA and add in a molecule of carnitine, so that you are going to have this molecule. This molecule is going to be called fatty acyl carnitine. Got this fatty acyl carnitine. But now another problem comes. Fatty acyl carnitine, we're going to have fatty acyl carnitine. It's going to enter through the carnitine translocase. Now this is a transporter called carnitine translocase. Fatty acyl carnitine is going to get into the mitochondrion. But now here comes the problem that fatty acid carnitine cannot undergo beta oxidation. So what are you going to do? We are going to remove the carnitine, replace it with a CoA. Now this is going to be done by an enzyme called carnitine acid transferase type 2. Right? It's located to the inner membrane of the mitochondrion. So it's going to release the carnitine, then add in a molecule of CoA. Carnitine is going to travel back because the transporter is a bidirectional transporter to the cytosol to catalyze another reaction. Then now we are going to have our fatty acid CoA, which is now ready to undergo the beta oxidation. Now, let's run through the beta oxidation. So, this is fatty acid CoA. This is fatty acid CoA. Right, and guys, something I forgot to tell you was that this initial step is called activation. The addition of CoA, ATP, all those other things are called activation. So that's the initial step. Then what we did here is called the carnitine shuttle or the transportation. So this second step here is the transportation. Then the third step is the beta oxidation. So I'm going to the third step, which is the beta oxidation. Now what is going to happen in the first step? We are going to involve the reducing components. So in this case, we are going to have the FAD. It's going to pick the hydrides. It's going to pick this hydrogen and this hydrogen here. So it's going to be converted to FADH2. It is going to be reduced. This plus. So FAD plus, let's call it the flavin, adenine, the nucleotide, is going to get reduced into FADH2. Alright, now what are we going to have? We will remove this hydrogen and this hydrogen so that we're going to have CH. We're going to introduce the double bond, then CH, C, S, H. Now, let me use a different color so that you can see together. Flavin, adenine, and nucleotide into FADH2. Alright. Now, what is the name of the enzyme that's going to catalyze this reaction? Now, you guys remember I told you that whenever you see these FADH, NADH, the NADPHs, we are going to involve a dehydrogenase enzyme. Now, this enzyme is going to be called acyl-CoA dehydrogenase. Acyl-CoA dehydrogenase. Alright. It is going to remove the hydride from this carbon and another hydride from this carbon. Then it's going to be picked by the flavin, adenine, and nucleotide from FADH2. Then you are going to introduce the double bond for that matter. Then let us move to the second step. The second step is going to involve hydration. So when you say hydration, you are going to input a water molecule. So we are going to input a water molecule. Now, what is the name of the enzyme that is going to catalyze this particular reaction? So this enzyme is going to be called enoyl CoA hydratase. So enoyl CoA hydratase is going to input a water molecule into this particular structure here. Now, what is the name of this molecule, which you just found there? This molecule is going to be called trans delta 2 enoyl CoA. Trans delta 2 enoyl CoA. Now see how this is going to happen. We say this is the first carbon, this is the alpha carbon, this is the beta carbon. Then it is in the form of a trans. You know, trans, then opposite direction, the hydrogen and the opposite direction. Located to the double bond, with respect to the double bond. Now let's move. So when you're going to add a water molecule with the help of enoyl CoA hydratase, you're going to form a new molecule. And this molecule is pretty cool. Now, we had our hydrogen here, another hydrogen here. But now when we add a water molecule, we're going to bring a OH here and that. Now let me use a different color so that you can see that very clearly. We're going to OH here and our hydrogen there. Alright. Now we get rid of the double bond because we have introduced molecules up there at the double bond. So this enzyme, or this molecule here is going to be called, now this is the first carbon, alpha carbon, the beta. is going to be beta hydroxy acyl CoA. Alright, that's going to be called beta hydroxy acyl CoA. Now we are moving on to the next step. So in this step, we are going to do what? We're going to remove the hydrates again. So this is another step where we're going to involve the reducing components. So what's going to happen? We're going to have a NAD plus going to be converted to NADH. That is nicotine amide adenine dinucleotide is going to be reduced into NADH. Now what's going to happen? There's an enzyme that's going to catalyze this reaction, and this enzyme is a dehydrogenase because you see you have the reducing components, right? So this enzyme is going to be called beta keto acyl CoA dehydrogenase. Now somebody might wonder where are you getting the keto acyl CoA? Now see this. The molecule that you're going to form here is going to be called R. Then you're going to remove. Now see this, guys. This enzyme is going to remove this hydrogen and this hydrogen. Alright, so what are you going to form? We are going to form R, C with a double bond, right? Then C, H, C, O, CoA, S, H. The first carbon, the alpha carbon with the beta. You know these are keto. This is a keto functional group. So what are we going to call this? This is going to be called beta keto acyl CoA. That molecule is going to be called beta keto acyl CoA. Alright guys, we are moving on to the last step in beta oxidation. Alright, now what is the name of the molecule that we are going to form here? So in this last step, we are going to involve a particular molecule, and this molecule is going to add in, it's going to do two functions. It's going to add in a molecule of CoA, and it's also going to cleave. So what is going to cleave? It's going to cleave the bond between the alpha and the beta carbon. So what are you going to form? Let us now see what we are going to form here, guys. This molecule is going to cleave this bond here. Let me show it in the different colors so that you can see. It's going to cleave that bond. So I just want to lengthen this arc so that you can exactly see what's going to happen. So I'm going to produce two molecules. So let me just add. Don't get confused, guys. I'm just, you know, add is a carbon chain. So I'm just lengthening so that you can now see exactly what's going to happen. Now I'm here. See. Now this enzyme that I'm about to say its name is going to introduce a CoA onto the beta carbon. So I'm going to have a CoA SH. I hope that's very clear. So what I've done is I've just lengthened the R group. Alright, what's the name of another molecule? Now it is this particular molecule here. So it's going to it has a hydrogen and a hydrogen. It's going to take up another hydrogen so that it can form CH3. So it can be CH3, COA, SH. And guys, this looks so familiar. What's the name of this? This is called acetyl CoA. This is called acetyl CoA. You know where we found this? Guys, in the tricarboxylic acid cycle. Hope you guys remember that. Now, what's the name of this molecule? If you look very clearly, this molecule is the same as this molecule, but it's only that it is 2 carbon short. Yeah, so this molecule is going to be taken up to the next round of beta oxidation. Now, this is called fatty acyl CoA. Now, it was a 16 carbon palmitic acid. Now, we have removed the acetyl CoA in the first round of beta oxidation. Now, we are going to remain with the fatty acyl CoA, which is now 14 carbon. You remember that? Yeah. It is 2 carbon short. We remove the acetyl CoA. Now, we're going to get back to the second round. It's going to come up 12, 10, 9, 8, sorry. 8, 6, 4, until we degrade the entire fatty acid to form acetyl CoA. Now, Somebody might wonder, where are you going to take all these things, acetyl-CoA, everything? Now, I'm about to show you in a minute. Now, where we are going to take the acetyl-CoA. Now, I'm sorry guys, I need to read the name of this enzyme. The enzyme that catalyzes this reaction is called thiolase enzyme. Thiolase. Alright. Thiolase is the one that does the cleavage of the bond here and also addition of the CoA. And that is why we got the name beta oxidation. Right? But I want to have written it here. It's called beta oxidation. Because we are going to click the alpha beta bond. So it's called beta oxidation. The enzyme thiolase catalyzes that reaction. Fatty acid CoA goes over and over again until we remove the entire, get rid of the entire acetyl CoA present in the fatty acid. Now, we are going to take acetyl CoA, it's going to come into the, acetyl CoA. Let me just show you how it's going to work. So, we have acetyl CoA. Let me just say acetyl CoA is going to leave the molecule of oxaloacetate, then form citrate, then isocitrate, then alpha ketoglutarate, then succinyl CoA, then fumarate, then malate, then oxaloacetate. Now, what is this circle here? This is called TCOA, or the Krebs circle. Now, that is acetyl CoA. Get into the tricarboxylic acid circle. Now, guys, what are you going to form from these circles? You are going to form Na. Let me just write them here. NADHs. You are going to form the FADH2. You are also going to form ATPs. These are not the exact ones that are going to get this molecule, just we are going to get them within the TCA. Now, the NADHs and the FADHs and ATPs, where are they going to? They are going to go to the electron transport chain. Electron transport chain. So, to yield energy in form of ATP. These are precursors in the electron transport chain. They are going to unload the hydrides, which can then undergo a series of oxidative reactions to generate energy in the process called oxidative phosphorylation, guys. Now, what was the main thing? We started from the mobilization of triglycerides. We were short of energy. There was low carbohydrate level, or in the fasting state, and maybe you're feeding a ketogenic diet or something. So you have a low energy level, there's low carbohydrate. So we needed energy to run a series of reactions in the body. That's why it broke down the fats, the fatty acids. The triglycerides. To get these particular components, we run them through the beta oxidation. We get the precursors, the NADHs and the FADHs and a bit of ATP to the TCA. Then take it to the electron transport chain to yield energy in form of ATP. Now we have solved the problem. The body has now enough ATP. And now what guys you need to know is that lipids or the triglycerides produce a lot of energy more than the carbohydrates. So the body is going to get a lot of energy to run a series of reactions within the body. Alright, what is left guys in this? I don't think there's anything left in this video. So in our next video, there's something guys, I want to tell you this. For example, we ran the palmitic acid. Now palmitic acid, is a 16 carbon. So somebody may wonder, how many acetyl CoA are going to get, how much ATP are going to get for that matter. Now let us see. We have a 16 carbon, I should just do it here. Forgive me this. 16 carbon. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 carbon molecule. Now guys, what's going to happen? I told that acetyl CoA has 2 carbons, so I'm going to remove 2 carbons at a time. So this is 1, 2, going to cut there, 1, 2, cut, 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 1, 2, cut. So how many acetyl CoA are you going to get from there, guys? We're going to have, let us count. 1, 2, 3, 4, 5, 6, 7, 8. Pretty good. We are going to have 8 acetyl CoA. Acetyl CoA. Alright, then we are going to go how many rounds to break down the palmitic acid. Now let us come and count the rounds. We are going to have 1, 2, 3, 4, 5, 6, 7. That's nice. We are going to have 7 rounds. 7 rounds. And this is very important, guys, because the 7 rounds are going to tell us the number of NADHs and FADHs we are going to obtain from the oxidation of a particular fatty acid. So it's a very easy way to know the number of rounds and number of acetyl-CoA. For example, when your professor gives you maybe to break down 26 carbon fatty acid, just going to divide 26 by 2, you get 13. That is the number of acetyl-CoA you are going to obtain. Then to get the number of rounds, you're just going to less 1. So maybe if it is 26, divided by 2 is 13, then less 1 is 12. So we are going to have 12 rounds. So it is that 12 that's going to tell you the number of FADHs and NADHs you are going to get, so that you will multiply maybe 1.5, 2.5 to get the exact amount of energy they contain. Hope that guys is very clear. So in our next video, we are going to see how we are going to calculate the energy obtained from the 8 acetyl-CoA and the 7 rounds, meaning 7 NADHs and FADHs, so that you can know the exact amount of energy we are going to get. And guys, that is it for this video. If you found this video helpful, please subscribe to my YouTube channel, comment and like. Let us meet in our next video, and please stay tuned so that you can know exactly what is going to happen, how we are going to calculate the energy produced by the oxidation of a palmitic acid. Thank you.